Okay, in this lecture we're gonna see about electrostatic. So before we begin with electrostatic, we need to know Coulomb's law. Okay. So it states that the magnitude of the electrostatic force between 2 point charges product is directly proportional to the of their charges and inversely proportional to the square of the distance between them. No need to be confused with any kind of wording here. It's just they are explaining this equation in a wording form. Okay, so the equation is F is equivalent to K times by Q1 Q2 over R, where Q1 is the charge for the first electron or first point, and Q2 is the charge for the second point, R is the distance, and K is this variable here. Okay, should be it's the, if you notice here, this is 4 pi E, where E is the permittivity. In air we declare the permittivity of E, we declare the total 4 pi E as 8.99 times 10 power of 9, but in some cases we make this as K, which is equivalent to 9 times by 10 power of 9. Okay, this is how the 4 pi permittivity became K, and such as 9 times 10 power of 9. Remember, the K value would be given. If the K value isn't given in the question, then you should write the K value as 9 times 10 power of 9. So in some cases the K value is given as 8.99, so beware of that. Now in this specific lecture we are going to know and talk about electric field before we move into capacitance. Okay, so electric force is much stronger than the gravitational force. Okay, in a certain period of time in electromagnetic theory, you need to understand this, as well as the total electric field is sum of individual fields. Okay, so E1, E2, E3, we may have many E, so the composed E, the total E is E1 plus E2, the sum of it. Okay, now what is electric field? Electric field is something that can be associated with each point in space and the unit of it. Maybe if we have a graph, then we have E here, we have E here, we have E here. So electric field is the combination of these three E's. Okay, then we have electric field due to multi-point charges. Now this is something you need to remember. Okay, the original equation is now if you notice, we have R1 here, then we have R2, then it goes, so it means that it can be expanded into R3, R4, R5 and so on. Right, now the example question that can be given for electric field due to multi-point charges are, okay, so the question could be something such as a charge of Q1 of 4 microcoulomb is located at 030, and then we have our Q2 in negative 2 microcoulomb 400. Okay, now find the total electric field at the origin at 000. Okay, now we know that Q1 is in this position, so our R1 is 0AZ or 0Z hat plus by 3Y hat plus by 0Z hat, so we only have 3Y. Now R minus R1, this is our origin R, so 0 minus 3 is automatically negative 3Y hat, negative 3. So R minus R1 with modulus becomes 3 and R square becomes 27. Okay, this is where it becomes the R square. Now for Q2, if we write R2, we will get that it's 4x hat plus 0y hat and 0z hat. Now R minus R2 becomes negative 4x hat. So the modulus of it is negative 4. Modulus of it would be, or you could write the vector, it's quite safe, would be 4, and R cube would be 64. Okay, now if you still remember, I mentioned that this one would become as k, and k would become 9 power of 10 9, or in this case we assume it's 8 9 9 10 9. Okay, now if you remember back, the original equation was as such: at q1 r minus r1 by r minus r1 cube plus by q2 r minus r2 modulus of r minus r2 cube. Now we didn't expand this because we only have q1 and q2, 2 points. So r1 and r2 we have 2. If we have 3, then we sum it with q3 r minus r3 modulus of r minus r3 cube. Okay, so we don't have it, we limit it till q2. Now this is declared as k, which is 8.99. now just replace the number 8.99 10 power of 9. Now q1 was given as 4 microcoulomb. Okay, now we know that r minus r1 is 3y, negative 3y. Okay, we need to write it in the vector form. Then we know that this was 27. Then we have plus q2 is negative 2. Then we had x hat 64. Now if we calculate this, remember this is still in vector form. Okay, if we calculate this, we will get as and then if we expand this, we will get the total electric field as Vm. Okay, this is the total electric field due to multi-point charges. This is the total electric field charge. Now this is for the multi-point charges. Now if we see, there are certain stuff that we need to remember. First is this equation where this could be changed as k, which is equivalent to 9 times 10 power of 9, or in some cases 8.99, and here this would expand depending on how many q's we have. Okay, now before we continue to our next part, the capacitance, I need you guys to remember these 4 laws. Okay, first is Gauss law. Gauss law for electric field tells that electric charges create electric fields. Positive charge blasts outward and negative charge sucks inward, meaning that positive charge sends the ray or electric field, the field line outwards, whereas the negative pulls it attracts. Okay, remember, negative always attracts, positive repels. Just remember it in a simpler term, but it's not the actual term, not to be confused. Then we have the Gauss law for magnetism, where magnet monopole does not exist. Every line comes back, 2 poles. So remember, magnet, we have a north pole and south pole. If you break, maybe if you cut it half here, it becomes 2, north south and north south, meaning that it has a line, something like this. Okay, so what does it mean? It means that if you break this Kit Kat into 2, it becomes as such. It doesn't becomes this n into somewhere, it should return back, which means ns, it's returning back. So it's not available in monopole. Okay, then we have Faraday law, which is for induction. A changing magnetic field creates electric field. like hydrodam, wind turbines, a changing magnetic field. Remember, for example, you have a coil, then you place a magnet. So the magnet field is around here, but if you change the magnet field, you move it here. For example, here is the south, but when you move it, here becomes the north. So when you move back and forth, this coil create, okay, due to this magnet moving here and here, this coil has an electric field around it, which is the application for wind turbines and also hydrodams. Okay, next is the Ampere law for current. Just now we say that changing magnetic field creates electric field. Moving electric charge or electric field, changing electric field, changing magnetic creates electric, changing electric create magnetic field. So for example, a coil, okay, a coil. So here is the starting point, here is the ending point. If a electron is moving, this has the electrical field, meaning it's the electric field is changing, it's going around and around. Here there are a magnetic field that is being created, it's invisible to the naked eye. Okay, so changing electric field creates magnetic field, changing magnetic field creates electric field. Okay, these are 4 laws that need to be known. Gauss law for electric field is where electric charges positive blast and negative attracts. Gauss law for magnetism say it doesn't has monopole. Faraday law for induction says moving magnet creates electric. Ampere law for current says moving current creates magnetic. Okay, now what is a capacitor? A capacitor is a storage tank for electrical energy, or in simpler term, a capacitor is equivalent to a battery, but this is not the exact wording that you can use. Okay, so capacitance is calculated by using this specific formula where Q is charge on one plate and V is the voltage across the plate. Now what is capacitor? Okay, this is the definition that's rooted from the textbook but using my own wording. Two conducting bodies, meaning it could be steel or it could be anything that conducts electricity, with non-conducting body in between, meaning if we have two plates, okay, this is plate 1 and plate 2, and here is air doesn't conduct electricity. Okay, so conducting bodies, two conducting bodies, so 1 and 2 with non-conducting body in between, which is air in this case, creates capacitance. So this creates capacitance. A DC power, maybe we connect it with plus and negative here, charges both sides. So the positive goes here, negative goes here, so it charges with positive ions here, negative ions here, with polarity, meaning here is the positive, here is the negative, creates electric field. Okay, so here this is the battery. If you charge positive and negative, this becomes a battery too, where it's separated. Okay, here is the positive ions, here is the negative ions. Push pull force in between them create electric field, so they will be pushing and pulling. Why? Because positive and negative attracts, so we have a energy field here, which is the electric field. Now if we disconnect this, okay, now if you are charging, it's getting the ions. If we disconnect it, it will become like this, doesn't loses charge. So the charged mechanism, charged ion are still here. Just because it loses the charging mechanism doesn't mean that it's losing its ions. The positive ion and negative ions are still here. When we, okay, it's near. Okay, now if we make it more further apart, the higher the voltage becomes. Okay, now these are the stuff that you need to remember, where it will be helpful for you to see here. Now as I said, this is the plate 1, this is the plate 2, so positive ions are here, negative ions are here. The more further you repel it, the more higher the voltage would be. Okay, and here is the electric field that has been created. Now this is a example of capacitance in a very understandable, very appropriate diagram, where this is the plate 1, this is the plate 2. Okay, this is the E field in between. Now a question would sound, as such. Obtain an expression for the capacitance of parallel plate capacitor comprised of two parallel plates, each of surface area A separated by D and the permittivity E. So we need to have C by using A, D and E. So we need to express an expression for C using A, D and also permittivity E. Okay, if you notice here, this is the diagram that has been given. Okay, so we have V voltage. Okay, then we charge it in both sides. Okay, then we have Z. Where does Z come? Okay, wait for a while. Then we have E, the electric field. Now if we refer to here, we have A, checked. Then we suddenly have Z to D. Okay, maybe check. The permittivity is not there, the C is not there. Now how to solve this question? So capacitance of parallel plate capacitor. Okay, so capacitance of parallel plate capacitor. Now before I begin, I would like to explain you guys certain stuff that you need to remember. Now we have two plates. As such, the definition for capacitor is we have plate 1, we have plate 2, two conducting bodies in between a non-conducting medium. So P1, P2 and here is the air. Now assume that P2 is in the graph of XY, meaning in a 3D platform. Okay, in a 3D platform, so this is X, this is Y, this is Z. So in a 3D platform, Z is 0 now. So we have put the metallic body here at the ground. Then another metallic body is above it. Okay, maybe somewhere above it. Okay, this is in the 3D diagram. So we know that Z is 0 here underneath, and here Z is something. So we know that the distance between here, the distance between two plates is declared as D. So Z is equivalent to D, which means that Z is 0 here. From the origin, we are putting the second plate above it. Okay, above it. So above it is equivalent to D, which is mean the distance between both of them. So Z has D. Now if you remember, here is the positive charge, here is the negative charge. So in between positive and negative, we have the electric field E. Okay, now if you remember, the diagram above shows that Z is D and here is E. Okay, now alright, now is the main part. They ask us to express C in the form of permittivity, area and distance. Now we need to know that electric field is equivalent to PS over permittivity, where PS, the capacitance, is equivalent to Q over A, where the E is equivalent to Q over permittivity and A. Okay, the second stuff you need to remember is V is equivalent to the difference of D to 0 for E, the electric field. Okay, so V is equivalent to E D, which means this E by this D is equivalent to voltage. How the hell? V is equivalent to electric field times by D. V is the product of E over D, distance and electric field, which is quite easier. Okay, so for the first one, you just need to remember this. Electric field is equivalent to charge by permittivity and area. What does it mean? You have two bodies. Okay, so the electric field is equivalent to one charge. If you noticed here, I have mentioned that charge on one plate, voltage across the plate. Okay, so the electric field is equivalent to charge on this plate by the area of the plate. If the area is small, so it's small. If the area is big, it's big. So the charge and area, the charge by area. Okay, what does permittivity stand for? I said that here is air. Maybe if we put oil, does oil conduct electricity? God knows. So oil has a different permittivity. Now electric field is equivalent to charge by permittivity and the area, permittivity and the area of the plate. Now the second is voltage is equivalent to the electric field over the distance. Now third is our initial, C is equivalent to Q over V. Right? Now this, we know that capacitance is equivalent to the charge over the voltage, charge on one plate. Now voltage is equivalent to ED. Okay, now E is equivalent to permittivity, meaning Q over permittivity A and D. So this one, if we do it in the exact order, we will get as such. So this is the answer. Now how do we get the answer? First, electric field is equivalent to Q over permittivity and area. The second one is voltage is equivalent to electric field and the distance. 3. C is equivalent to charge over voltage. So charge over voltage, we know that charge over ED. ED is the voltage. Now the next one is Q over, we know that electric field is equivalent to Q over permittivity A and D. This one, if you do the fraction, you will get permittivity A over distance. So this is the answer. If you want to write in a normal wording to explain this diagram, it's good. So this is for the electrostatic, and we'll see